It was summer 2024 and huge advancements were being made in the field of photovoltaic solar panels. With huge gains in efficiency and cost reduction, I knew that I had to do a project involving this rapidly developing technology. My plan was simple. I wanted to design a device that allowed a solar panel to follow the sun as it moved through the sky, charge my phone, and store any excess power generated in an external battery. Essentially, I aimed to build a miniature renewable energy grid with electricity storage. Most solar panels are comprised mostly of large, single crystals of silicon. In one part of the crystal lattice, atoms with a high number of valence electrons are added, forming the N region. In another part, atoms with few valence electrons are added, forming the P region. The N and P regions touch, and the place where they touch is called the depletion region. A solar panel works in the opposite way that an LED does. When light hits the depletion region, electrons accumulate in the N region, and holes, or simply a lack of valence electrons, accumulate in the P region. It is common knowledge that opposite charges attract and like charges repel, so the electrons in the N region want to get as far away from each other as possible. This repulsive interelectronic force can be used to power a circuit that is connected to the panel. After completing their journey through the circuit, these electrons combine with the holes in the P region and annihilate. This is a fancy way of saying the electrons are absorbed into the valence shells of the doped atoms in the P region. This allows for the electrons to keep moving as long as there is a sufficient amount of light striking the depletion region. At higher temperatures, electrons move more randomly than they do in the direction of the current through the circuit. Remember this because it becomes important later. Since more power can be generated when more light hits the solar panel, it makes sense to have the solar panel reorient itself throughout the day to make sure that the panel is always facing the sun. My first order of business was to choose a solar panel. To charge a device over USB-C, the potential must exceed 5 volts, but not be too much higher than that so as not to destroy the device being charged. For reasons I will explain later, I wanted the panel to operate at 6 to 8 volts and have at least 10 milliamps of current so that I can measure the output of the panel. The 6 volt 2 watt panel by Voltaic Systems caught my eye due to the comprehensive data sheet written by the manufacturer. I did not completely trust the third-party vendors selling this solar panel, so I tried to simulate the device using LT-Spice and the parameters outlined by Voltaic Systems in their data sheet to see if it would still meet my specifications. A photovoltaic cell can be approximated by connecting a current source, a diode, and 2 resistors as shown. The resistor parallel to the diode is the shunt or short circuit resistance, and the other resistor is the series resistance. I was unable to find these parameters in the data sheet, but I could experimentally determine them if I had the physical panel. I emailed the manufacturer, but they were unable to help me. I was stuck in a paradox where I did not want to commit to a purchase until I knew the specifications of the product, but I could only find these specifications if I had the physical panel. Fortunately, there was another way for me to determine if the panel would meet the voltage requirements. The figure on your screen is called a voltage current or IV curve. The blue line shows the current at different voltage values, and the orange line shows the power at the current voltage pairs for this panel. This comes straight from the manufacturer. You're probably thinking, oh, this is great, Alex. You can clearly see that there is a decent amount of current being produced at 6 volts and above to account for resistance. That means this panel can be used in the device. Well, it's actually more complicated than that. You see, this voltage current graph was calculated in southern Florida at noon in the middle of July on a clear day. Additionally, the panel was kept at a rather chilly 25 degrees Celsius. The luminosity the panel was exposed to was roughly 1,000 watts per square meter. Remember, a panel exposed to a lot of sunlight would be able to generate more current and at a higher voltage than a panel that receives less sunlight. I wanted to test my design outside in mid to late August between 10 a.m. and 2 p.m. in Hamilton, Ontario, Canada, which is only slightly closer to the equator than it is to the North Pole. I expected the temperature of the panel to be higher than the manufacturer's IV curve as well. According to this website that I was able to find by a group called Engaging Data, my simulation would occur between 770 and 600 watts per square meter. If you know the IV curve at one luminosity, you can figure out the IV curve at any other luminosity. The equation on your screen shows how the current can be calculated given the current on an IV curve with a known luminosity. L naught is the luminosity with a known IV curve. L is the luminosity we are exposing the panel to, and I naught is the current with the known IV curve. As for voltage, V naught is the voltage on the known IV curve. N is a parameter called the ideality constant. For silicon monocrystal solar panels like this one, we use any value between 1 and 1.2. K is the Boltzmann constant, and T is the temperature in Kelvin. Note that these equations are approximations. On your screen, the blue line is the IV curve observed by the manufacturers under ideal conditions. The green curve is what I would be getting, assuming it was 25 degrees Celsius. As you can see, there is a staggering current reduction, but I'm still well over 10 milliamps at 6 volts. I then purchased the panel. The current produced and voltage supplied by a solar panel depends on the resistance between its positive and negative terminals. Throughout the day, the amount of light that hits the panel changes. Naturally, we want the most power from our solar panel, so we need a device called a Maximum Power Point Tracker, or MPPT. MPPTs are circuits that take some current at some voltage and output a combination of current and voltage that maximizes power. However, we are not looking for a true MPPT. Since we are charging a battery, we want the highest power that is between 6 and 8 volts rather than the point on the IV curve yielding the highest power. I decided to use the Solar Power Management Module MPPT by a company called Waveshare, since few MPPTs worked at such low voltages. As an added bonus, there was a DC002 jack that allowed me to directly attach the aforementioned solar panel without the need for soldering. To accurately follow the sun throughout the day, a solar panel needs to rotate about 2 axes. In spherical coordinates, we would say that there needs to be rotation in the theta and phi directions, or to put it simply, there must be horizontal and vertical rotation. I purchased 2 MOT28BY48 stepper motors since I already owned one model and I was taught how to operate it in the course CompEng 2DX3. Full disclaimer, these motors are notoriously weak, but draw very little current. I used 2 motors near the top of my design in order for the panel to rotate in the theta direction, since these motors would have to work against gravity. All motors were used in the full step method of operation since it allows for the most torque. These motors need 5 to 12 volts to operate. To power the motors, I stripped a USB cable and split the 5 volt and ground wires into 3 separate paths. The USB cable was plugged into my laptop during testing. But Alex, you say, how will the motors make the panel face the sun? Almost every dual-axis solar tracker has a T-shaped protrusion that is used to orient the device facing the sun. My design is no exception. This T-shape works similar to a sundial. When the device is not completely facing the sun, some quadrants are covered in a shadow more so than others. A photoresistor is a circuit component that increases its resistance when it is exposed to more light. If a photoresistor is placed in series with a resistor, a voltage source, and the ground, then its voltage will increase when it is exposed to more light. By connecting the device to a microcontroller and reading the voltage values, photoresistors now act as an analog to digital converter. By rotating the panel in the direction that yields the highest voltage, the device can be kept facing the sun throughout the day. I bought a pack of 40 photoresistors off Amazon, and it will be in one of the links below. You can design a proper dual-axis, Wi-Fi independent solar tracker with only 3 photoresistors, provided that you do not put them in a straight line. I decided to use 4 since it made the programming easier and had no impact on the cost since I had to buy 40 photoresistors anyways. I used a 1 kilo ohm resistor with each of these photoresistors since this resistance value allowed me to use as much of the 5 volt analog input pin voltage range in a variety of brightnesses. What you see on your screen now is the output window on my multimeter of me playing around with the photoresistors, bringing my phone flashlight up to them and then away from them. This test is what made me decide to use a 1 kilo ohm resistor. The brain of my device was an Arduino Nano since I only really needed 14 GPIO pins. I purchased a 3.6 volt 2100 milliamp hour battery to store any excess electricity that I generated since the MPPT allowed for this, but this step was completely optional. I also purchased a dual action USB multimeter and power logger since I wanted to measure the performance of my design. The data collected by this device would be sent to my old second laptop since my current laptop only had two USB ports that were taken by the motors and the microcontroller. If you are going to build this yourself, I have included links to all the devices I purchased. I designed the mount for the device myself in Autodesk Inventor, and I have included the STL files that I 3D printed. I have also included the circuit I used and the code. I have also included a testing program used to view the values inputted into the circuit by the photoresistors. This was a valuable debugging tool that saved me a ton of time. Be mindful that you will need to wire the top two motors in opposite order on the stepper motor drivers since they are facing each other. Clockwise on one motor is counterclockwise on the other. Also, make sure that you set the MPPT to 6 volts by flipping the switch on the back of the device. All components were either soldered, hot glued, or taped together and secured on top of a piece of cardboard for stability. The first test took place indoors. I call this test motor abuse because I subjected the motors to way more rotation than they would encounter in a typical day. This test was to ensure that the device was capable of following a light source and untangling its wires by returning to its original position if it rotates too much in the positive or negative phi direction. No MPPT or charging accessories were included. This test took place in my bedroom using the light on my ceiling and my cell phone's flashlight. In the first few seconds, you see the wire untangling protocol. I then take a few steps back to show the panel pointed directly at the ceiling light. I then turn on my phone flashlight, which is held close to the photoresistors in order to overpower the ceiling light. I move the light around the panel to demonstrate the ability of the panel to track a light source and shake my phone a little just to make things a little more difficult for the device. You get to see the wire untangling routine a few more times. I end the test by turning off the flashlight and stepping back to show the device pointed directly at the ceiling light. I consider my design to have passed this test with flying colors. The second test took place outdoors with the MPPT accessories connected. It took place on a moderately cloudy August 21st at 4 p.m. and was meant to prepare me for the next day's test. Although the tree shadow is close, the device is kept in direct sunlight. Given the non-ideal simulation conditions, I was not surprised to see only 3.8 volts and 0.1 amps going into my phone. The third test took place outdoors between noon and 2 p.m. on August 22nd. The weather started out clear but got a little bit cloudy as the day progressed. The time lapse you see right now is the last hour of that simulation sped up 150 times. The first hour of footage had to be deleted because someone really wanted to talk to me. They were in the frame a lot and I wanted to protect their privacy. I did collect data for the entire 2 hours. You see me checking the power meter a lot and looking at the front of the device to ensure that the solar panel is still facing the sun. You're about to find out why. I was shocked by what I saw. The entire simulation saw a continuous voltage output of just over 5 volts. When the sky was clear, I only saw an output of 10 milliamps, and when the sun was blocked by clouds, up to 25 milliamps were produced. This was the complete opposite of what I had expected. While I was not surprised that the sunnier outdoor test saw a higher voltage, I was completely caught off guard by the fact that the highest output power occurred in the least favorable atmospheric conditions, and that less power was generated when the sun was shining. Let's see the IV graph again for 600 watts per square meter. Taking the area under the first 6 volts, we can see that we should see close to 1 watt of power generated. This is the actual power logged throughout the test. The device averaged a measly 0.054 watts and never produced even 1/5 of the power it was supposed to. I do have several theories as to why my device underperformed outdoors with no clouds. To start, the reason why I kept looking at the front of my device was to make sure that it was always facing the sun. I did see some very small shadows on the photoresistors, yet when I checked in my debugging program, the voltages across each photoresistor were more or less the same. Watch the time lapse again. That was 1 hour of footage. In a typical day, the sun moves 15 degrees across the sky in an hour. I don't know about you, but I don't think the solar panel rotated 15 degrees. Weber-Fechner law states that human brightness perception is a logarithmic scale. Although my bedroom light may have seemed, let's say, half as bright as the outdoor simulation environment to me, in reality, the luminosity may have been 100 times brighter outdoors. My theory is that there comes a point where adding more light does not increase the resistance of a photoresistor. I suspect that outside the luminosity is so great that the scattering effects of the air make it so that even in a shadow, the resistance, and by extension, the voltage drop across a photoresistor is close to the maximum that it can be. This could explain why the device was much more responsive to moving light sources in my darker bedroom than it was outside. Additionally, when I was playing around with the photoresistors in the oscilloscope, I could not get the voltage to change at all for the last 2 centimeters where I brought the light closer. My device would benefit from using photoresistors that did not saturate as quickly. However, as I mentioned, the photoresistor shadows were very small, meaning my device was probably only off by a few degrees, and this can't explain the entirety of the underperformance. Voltaic Systems did mention that they calculated their IV curves at 1000 watts per square meter, but they made no mention of the wavelengths used and their relative intensities. This is important because solar panels perform differently at different wavelengths. Perhaps my device's underperformance is attributable to different wavelengths at different intensities in my simulation environment when compared to the manufacturer. A typical sunny mid-July afternoon in southern Florida has a temperature of 32 degrees Celsius in the shade. It is likely that the manufacturer artificially cooled their panel to 25 degrees Celsius during testing. The weather forecast during both outdoor simulations was 27 degrees in the shade. It is safe to assume that the temperature in the sun was much higher than the 25 degrees Celsius that the manufacturer tested their panel in, especially when you consider that this panel is at most 22% efficient, which means that the other 78% of the light energy hitting it gets converted into heat. As a matter of fact, when I was packing up my device and other instruments, the solar panel was very hot. Recall that due to the random kinetic motion of electrons, solar panels are less efficient at higher temperatures. Let's see that voltage equation again, since current is not impacted by temperature. As we can see, the temperature term is multiplied by the tiny Boltzmann constant, so a hot panel likely cannot explain why the device underperformed on its own. A more likely culprit for the underperformance of the device is the MPPT, since it was easily the most complex circuit element that current flowed through. The device got so warm that I could barely hold it after the simulation took place. An already hot MPPT getting even hotter when the sun emerges from behind the clouds could explain why the device performed better under cloudy skies. The most likely reason why the device underperformed is USB handshaking. I was unaware of this phenomenon until after the project was completed. When devices are connected via USB, there is a brief period where the devices communicate with each other and negotiate how much current and voltage to send. USB-C charging protocols, like the one used in this project, operate at 5 volts minimum. The lowest current I could find on a device charged via USB-C in my house was 500 milliamps. Look at the 600 watt per meter squared IV curve. This solar panel is capable of reaching the 5 volts needed to charge a device via USB-C. However, it doesn't even come close to generating a current that this protocol is designed for, even when we neglect the resistance and other circuit components. My theory is that during the third test, there was enough power being outputted by the panel to undergo handshaking. This is why I believe the voltage always remained around 5 volts. I believe that to maintain such a high voltage for such a small panel, the MPPT was forced by the handshaking protocol to operate at a lower current and by extension, a lower power level. This might explain the scaldingly hot MPPT, since so much power was dissipated before even making it to the phone. During the cloudy second test, I doubt that there was enough power being produced to even undergo handshaking, so the device got away with outputting an unusably low voltage, yet more current and power. As you could imagine, I was very unhappy with a 54 to 95% error. For the amount of effort that I put into this project, I felt that I had no choice but to do one more test to determine why I got such awful results. I wanted to keep the conditions as close to the ideal as possible. This last test was taken on August 27th, 2024 at 2:13 p.m. There were no clouds blocking the sun and approximately 720 watts per square meter of sunlight. I manually pointed the device at the sun since I felt that I could not trust the photoresistors to orient the panel at such high luminosities. Given that I was highly suspicious of power losses from the MPPT and USB handshaking protocol, I removed the DC002 jack to expose the positive and negative wires connected directly to the terminals of the panel, and did not attach the USB power logger, phone, or MPPT. I wanted to measure the current and voltage from the panel and the panel alone. Ohm's law is the first equation students typically learn in their study of electrical engineering. It states that voltage is equal to current times resistance. Given that my oscilloscope can only measure voltage, by connecting a known resistance between the positive and negative terminals, I would be able to find the current and by extension the power by measuring the voltage. I wanted to get as close to the maximum power output as I could since my oscilloscope is less accurate at low power. At 720 watts per meter squared, I would need a resistance of roughly 28 ohms. I wired 10 330 ohm resistors in parallel to have an effective resistance of 33 ohms, meaning I would have a slightly higher voltage and slightly lower current compared to the maximum power point. The reason why I went with such a large current divider was because the resistors are rated at a maximum power of 0.25 watts. I knew I would be getting approximately 1.6 watts from the panel assuming everything worked properly, so I had to reduce the power across each individual resistor quite a bit. To my surprise, the error was reduced from 95% to less than 1%. This confirmed my suspicion that most of the power losses were the result of the devices connected to the solar panel rather than the panel itself. Although the device would take almost 14 hours to fully charge my phone in ideal conditions, I am still happy with how everything turned out. I found conclusive evidence that the underperformance of my design in some tests was caused by the prefabricated parts that I used and geography rather than design or programming flaws on my part. I had so much fun researching and designing this project. Renewable energy is an exciting field, and I can't wait to see the new ways humanity will find to harness the power of the massive 1.3 million kilometer wide nuclear furnace we call the Sun.